in our last little lesson that we did, we talked about Bronsted-Lowry acid base concept. So we talked about the theory behind our acid-base proton transfer, remembering that an acid is a proton donor while a base is a proton acceptor. And we looked at a few examples of what that might look like. Now, Bronsted-Lowry had a little theory that expanded on that a little bit in terms of the reaction of our strong acid and our strong base. So we're going to take a look at if there was a case where we have multiple acid or base entities in a reaction to predict which reaction is going to happen the most or which reaction is going to predominate. So when talking about those reactions and talking about collision reaction theory, which remember collision reaction theory is sort of like kinetic molecular theory where molecules are consistently moving around and a reaction occurs if those two molecules collide. So according to our collision reaction theory, a proton transfer may result from a collision between that acid and a base. So between this acid and a base, we're going to have some sort of proton transfer. But a proton will only transfer if an entity or an acid entity collides with a base entity that's a better proton attractor. So this base that it reacts with has to accept the proton better than the acid will hold on to it itself. So the acid's only willing to give up that hydrogen if the base pulls that hydrogen harder than the acid is. So therefore, when we're talking about acids and bases and the reactions that are going on, the only reaction or the predominant reaction will be between our strongest acid and our strongest base. So we're going to have to use our data booklet to figure out relatively which base and acid is the strongest that we have in our solution. So at this point, one thing I would recommend is to get your data booklets out and turn to page 8 and 9 in that data booklet to make sure you have all of your acids and bases and their relative strengths out beside you as we're going through to solve these problems. I would also recommend that if I'm going too quickly as I go through the lesson, make sure you pause. If you are a note taker, make sure you're pausing that lesson to make sure you have all the notes down that you feel necessary in order to move forward so that we're not getting too far ahead of ourselves as we go through. So we're going to try and work through this to figure out what is our strongest acid and our strongest base and how these are going to react with each other. So at this point, especially here, I would recommend pausing this video and writing these 5 steps down as you will use them quite frequently in this unit as well as throughout this course. So essentially, Bronsted-Lowry came up with steps in order to predict what acids and bases are reacting in our in our equations or in our empirical testing that we are trying to do here. So step 1 is to list all entities that are present. Now, when we list these entities, they can be, if it's an ionic compound and that ionic compound is in solution, so for example, if it's potassium hydroxide, just as an example, this dissociates, if this is aqueous, it dissociates into potassium and hydroxide. So when we list entities, we will list them as their ions, or if it's aqueous, we'll list it as potassium ions and hydroxide ions. Okay, if we're talking about an atom present, that would be something that's a pure element, okay, or a molecule, which would be something like water. Now, we don't write down that water ionizes, we write it down as a liquid. Okay, so once we have all of our entities listed, then we go and identify, based on our data table, all possible acids and bases, okay, using our definition of Bronsted-Lowry. Okay, step number 3 is to identify our strongest acid and our strongest base using our data table. So everything we do here, we have to have our data table out with us to check those acids and bases. Step number 4 is to write out an equation showing that proton transfer, showing that transfer from our strongest acid to our strongest base, and then predict the products made, because it should be a conjugate acid base as the product. So the conjugate base will be from our strongest acid and the conjugate acid will be from our strongest base. Step number 5 is to predict the approximate position of that equilibrium. So essentially this is asking us to figure out whether products are going to be favored or reactants are going to be favored. Because remember, when we're talking about these reactions, we're dealing with equilibrium. We're dealing with a forward and reverse reaction rate. So I know this might look like a lot, and I'm going to go through a question here, and we're going to go through step by step to really ensure we're understanding that we know what it means to list all entities and identify acids, bases, things like that. So we're going to go through an example in depth here. So our example says, what will be the predominant reaction, meaning reactants or products favored, so that forward or reverse reaction, if drain cleaner, being sodium hydroxide solution, is neutralized with vinegar. Now, vinegar is acetic acid. So when we go through, our first step will be to list all entities. So we have sodium hydroxide. Now, again, sodium hydroxide, NaOH, dissociates into sodium ions and hydroxide ions. Okay, and it says it's neutralized with vinegar. Now, vinegar is acetic acid, which is CH3COOH. Now, the one thing that's a trick in this question that we need to be aware of is that vinegar or acetic acid is dissolved in water, as well as sodium hydroxide solution is given in the question. So one thing we also have to list in this question that may not be that evident is water. We have to list water as an entity because we do know that water can act either as an acid or a base. So we have to list all entities present. So based on our example, these are the things that we have present. And again, I'll just write down this is acetic acid. So these are the only things that we have in our beaker or in our situation that's given. Sodium ions, hydroxide ions, acetic acid, as well as water. Okay, it's not super important to know the relative amounts of these at this point, just that they are present. Okay. Step number 2 is identify all acids and bases. So I'm going to just write down what we have from our first step. So we have sodium hydroxide, we have acetic acid, and water. Okay, so our second step then is to identify all things as either acids and bases. Now, remember, acids is a proton donor, and bases are proton acceptors. So essentially, I look at this and I say that we can have a proton acceptor here, and so that means that this will be a base. Now, I also know hydroxide ions are basic, so that's why I started there. When I look at sodium ions, I look and I say to myself, can it accept a proton? It can't really, because it's sodium with a positive charge, and a proton also has a positive charge, so it's not really going to want to accept that proton, as well as there's no protons to donate. Therefore, this is something that we'll just call a spectator ion, and we can simply draw a line through that. Generally, any positive ion that doesn't have a hydrogen in it will not be considered a part of our acid-base reaction. We can just call that a spectator ion, and we're going to cross it out. When we're dealing with acetic acid, well, as the name notates, we also know that this is going to be a proton donor, and we see that this H, this hydrogen or this proton, is likely going to be the one that's going to be donated. Now, from previous examples, we also know that water can either act as a proton donor, turning into hydroxide ions, so it can be a proton donor, or it can be a proton acceptor. We know that it can turn into hydronium, so we can get H3O. So this guy, we have to identify it both as an acid or a base, because according to Bronsted-Lowry's theory, we need to find our strongest acid and our strongest base. So in some cases, water can actually act as our stronger acid or base. So we always need to consider it and notate it as amphiteric and amphoteric by notating that it's both an acid and a base. So at this point, we need to definitely have our data booklet out. Now, if you're unsure to figure out which one of these entities is an acid or base, we can also confirm that by going to our data booklet and finding them listed in either the acid column or the base column. Now, again, note that, for example, I have water here in my base column at sort of the top, and then I also have water down at the bottom in my acid column here. So if it's in both columns, make sure I'm listing it as both an acid or a base. Now, when I'm talking about the entities that we've listed, which are acetic acid, so we'll find acetic acid on here. Why can't I find acetic acid? There we go. Apparently I'm a little blind right now. So we have acetic acid here, and the other acid that we're dealing with is water. Now water is down here. Now remember, our stronger acid is towards the top of this column. So water is our weakest acid, so therefore we're going to be dealing with acetic acid as our strongest acid. Okay, and our strongest base is something that falls near the bottom. So I generally start at the bottom and look upwards to try and find my strongest base, because my strongest base is going to be near the bottom. So when I take a look at that and I find my strongest base, well, I see here that hydroxide ions right here are our strongest base. So we have acetic acid as our strongest acid and hydroxide ions as our strongest base. Now, reminder that if something is in this left-hand column, it's considered an acid. So we see here that water is a very weak acid because our strongest acids are at the top, as notated by my purple arrow here. And water, in this case, is a very weak base because our strongest base goes from the bottom and works its way up. So when we take a look back at our example, we'll go to step number 3. And step number 3, again, okay, step number 3 says just identifying our strongest acid and base, and I'm simply going to go that this is my strong base and this is my strong acid. And I'm just noting it in a different color, but you can go through as you kind of go through step 2 as you get better at it. So my strong base is this hydroxide, my strong acid is my acetic acid. Now, step number 4 is to write out our acid-base proton transfer equation between our strongest acid and our strongest base. So we know that our strongest acid is our acetic acid, so CH3COOH. We're mixing that with our hydroxide ion. And again, I'm writing my equilibrium arrows. Okay, we get our conjugate base from our acid, our strong acid, which is our acetate ion, and we're getting water. Remember that there was this proton transfer in this direction. We've added this hydrogen to this hydroxide ion, giving us our equation here. Now again, as I go through, I should double check always that I've created a balanced chemical equation, ensuring that I've balanced both mass and charge. So here I have, on my reactant side, I have a 1- charge overall, and I have 5 hydrogens, I have 3 oxygens, and 2 carbons. Again, 2 carbons, 5 hydrogens, and 3 oxygens on this side. Again, negative charge, so we're all good. We've balanced this. Now, since we're just moving a hydrogen to a different entity, we should always be creating a 1:1:1:1 ratio. So I should never have to balance this mass or charge as long as I'm writing down my appropriate entities, both the acid and its conjugate base for both my products and my reactants. Should be a 1:1:1 ratio. Now, our last step that we have is to determine the position of our equilibrium. Now, this is something that I also like to add into my data booklet, and I'll show you where I'd write that in a minute here. But essentially is if we consider this image here that I have on the side, that we have our products favored, and we think of these as columns. So if I think of this as my acid column and my base column, or my conjugate base column, if my stronger acid, or my strongest acid, is above relatively, now this can be at any level of being above, as long as it's not parallel to that strong base, as long as it's above it in the table, okay, as long as my strong acid goes to my strong base down, and I call it going down the river, then this is a products favored reaction, or it's greater than 50% favored. Okay, again, if we can continue these columns and consider that this is still my acid column and this is still my base column, that if my strong acid, I might do this in a different color here, if my strong acid is below relatively to my strong base and I have to climb up the river, then my reactants are favored. It's a less than 50% reaction. So if we go back to our data booklet here, on the side somewhere, I would add in, let's just do that here, that if I have my strongest acid to my strongest base, I would say products favored. Okay, and you might want to write products favored. Okay, and then here I'm going to say reactants favored. I'm going to abbreviate a little bit so it can all fit in. That my strongest acid is below my strongest base. So when I look at my example that we've been working on here, if I find my strongest acid being acetic acid, and I'm always comparing the right side relative to the left side. So this looks like I'm going down the river. Okay, if I'm flowing down the river, I'm looking at a products favored reaction. I'm looking at my strongest acid being above my strongest base. Okay, I would take your fingers out and point to your strongest acid, point to your strongest base, and compare your fingers when you're looking at them to definitely give you a visual that this is higher up in your table compared to this. Therefore, it's a products favored reaction. So when I go back to my example, okay, when I'm talking about the position of our equilibrium, I want to notate this in a few ways, and there's a few ways to do it. So I have, again, my hydroxide ions. Oops, I started with the other one here. Okay, I have my acetic acid. I have my hydroxide ions, my equilibrium arrows, and I get my acetate ion. And I've got my water molecule at the end there. Now, the way that I can notate this in a few ways, either I go above my equilibrium arrows, greater than 50%, which is acceptable, perfectly fine with that, or I can also write below that products are favored. Okay. So those are the 5 steps, breaking it down, going through to determine the position of the equilibrium, or whether products or reactants are favored, or in other words, if our forward or reverse reaction rate is favored. Okay, a few other things that you might need to know or consider is that hydronium ions is the strongest known acid. Okay, it's the strongest known acid entity that we have. Therefore, our 6 strong acids are all written as H3O, and this should have a little positive sign in there, H3O positive when in aqueous solution. So that's something to keep in mind for sure. Now, our hydroxide ion is our strongest base that can exist in aqueous solution. Again, our base is in the bottom right corner of that table. As well as no entity in aqueous solution, aqueous, remember, meaning dissolved in water, can react as a base if it's a weaker base than with water. Okay, therefore, its conjugate base is not considered really a base in aqueous solution. So I'll explain using the data table what I'm talking about here. If we go up to the top, any of these 6 acids that are listed here, okay, 1, 2, 3, 4, 5, 6, we never write them as this in our entities when we list them. Okay, if we have perchloric, hydroiodic, hydrobromic, hydrochloric, sulfuric or nitric acid, we only notate them as an entity as hydronium ions or as H3O positive. All right, now another thing that I mentioned there in the previous slide was that any of these conjugate bases of our 6 strong acids, they are all going to be dissolved in water because our acids always have to be dissolved in water. Now, what you'll notice is as we go down the table, we have stronger and stronger bases. But what do we see here is that water is a stronger base than any single one of those conjugate bases. Therefore, if you have one of these as a base, we always use water because water is going to be a stronger base than any single one of those entities. So again, if you have one of the 6 strong acids in solution, when you list it as an entity, you list it as hydronium ions. And again, if you have a conjugate base that of one of those strong acids, you will not even list it in your entities. Well, you can, but you'll kind of ignore it, and you'll use water as your stronger base there. Oops. Let's just go back to our presentation here. So, one more example. I'm going to go through this a little bit quicker, a little bit more fluid, just to go through the steps one more time to get a better idea of what we're talking about here. So, oops. There we go. Okay. So I have hydrofluoric acid. Now I should double check that this is not a strong acid because again, if it was, I would write it down as H3O and sure enough, it's hydrofluoric acid is just a weak acid, so I record it as hydrofluoric acid and an aqueous solution of sodium sulfate. So I have sodium and I have sulfate. And it's in an aqueous solution, so I always have to include water there. Okay, and they're mixed to test the 5-step method predicting our acid-base reaction. So we're going to see what we can discover here as we go through. So we have hydrofluoric acid, which is our acid. We have sodium. It cannot be a proton donor, nor it can be a proton acceptor. Okay, this guy looks like he could probably accept a proton. He looks like he has negative charge. A proton can fit in there, and this can accept that proton, therefore it's a base. Okay, I can also check my data booklet, but that's a good logic to say it can accept a proton. And this water, we know, can either accept a proton as a base or donate a proton as an acid. So there's our second step there. Now when I check my data table, which I will do, I'm going to just see which entity is my strongest acid, my strongest base. So, oops, here we go. Oops, wrong way. I see that hydrofluoric acid is here, water is below here, and water is above my sulfate ion. I do believe. So here's my sulfate ion, which means it's acting as a stronger base than this water ion, or water molecule, pardon me, is here. So my sulfate is acting stronger than this water, and also this hydrofluoric is acting stronger than the water in my other example, or as an acid. So when I take a look, this guy is my strong acid, and this guy is my strong base. So my third step is done, and now I'm going to take a look at step number 4, which is just writing out that equation. My hydrofluoric acid is reacting with my sulfate, and we're getting the fluoride ion, and our hydrogen sulfate. Okay, now when we take a look back at our data table, we just want to double check which entity lies above the other one. So here is our hydrofluoric, here is all our sulfate. So when we're talking about these things, we're always looking at our reactants. We're not looking at our products. We see that I have to climb up the river. I'm going upwards when I compare my acid to my base, meaning that my reactants must be favored. So when I go back and write that in my equation here, all right, I write that reactants are favored. I can write it as less than 50% reaction, or I can say reactants favored. Like so. So those are some examples on how to predict our Bronsted-Lowry reactions, our Bronsted-Lowry acid-base proton transfer reactions, and there is a little bit of a worksheet to go through in order to practice some of these questions, followed by an answer key that you can get from your teacher. All right, good luck.